Hello everyone. In this video, I'll discuss the differences in NMOS and PMOS transistors, focusing on key characteristics such as switching speed, resistance, noise margin, and power efficiency. Before diving into the characteristics, let's first understand the 2D structures for NMOS and PMOS. The NMOS transistor consists of N plus doped source and drain regions, a P-type substrate, silicon oxide insulator, and polysilicon gate. When the source is connected to ground and a positive voltage is applied to the gate, a conducting channel forms beneath the gate, allowing current to flow between source and drain. Conversely, the PMOS transistor consists of P plus dope source and drain regions, N-type substrate, silicon oxide insulator, and a polysilicon gate. In PMOS, the source terminal is connected to VDD, and when a logic 0 is applied to the gate, a conducting channel forms, allowing current to flow between source and drain. To better understand the NMOS and PMOS characteristics, let's first look at how N plus and P plus regions are formed. To obtain an N-type or N plus semiconductor, dopants are introduced into this intrinsic silicon crystal lattice to alter its electrical properties. N plus regions are created by doping silicon with a group 5 element or the elements which have 5 outer electrons. Primarily, phosphorus is used. Phosphorus with atomic number 15 has electrons distributed as 2, 8, and 5 in energy shells. When phosphorus is introduced in the silicon lattice, 4 electrons bond with neighboring silicon atoms. The 5th electron is weakly bound and requires very little energy to become free. At room temperature, thermal energy is enough to free this electron, making it charge carrier. Once an electron is released, the phosphorus atom is positively charged ion, remaining fixed inside the lattice. Since free electrons are mobile, they become the majority charge carrier in N plus doped silicon. Now for PMOS. In PMOS, the P plus regions are created by doping silicon with a group 3 element or an element which has 3 electrons in the outer shell. Most commonly, boron is used. Boron with atomic number 5 has electrons distributed as 2 and 3 in energy shells. When boron is introduced in silicon lattice, 3 electrons bond with the neighboring silicon atoms. Boron captures an additional electron from nearby silicon atom, leaving behind a hole in silicon atom. As electrons move in valence band, holes appear to move in opposite direction. Since holes act as a majority charge carrier in doped silicon, these materials are called p-type semiconductors. Now let's go over the differences in NMOS and PMOS characteristics. First, the switching speed. NMOS transistors switch faster than PMOS transistor. This difference in switching speed is primarily due to mobility of charge carriers and intrinsic resistance of the MOS transistors. NMOS transistors use electron as charge carrier while PMOS transistors use holes. Electron mobility is about 2 to 3 times higher than the hole mobility in silicon. Higher mobility means that the NMOS transistor can conduct current more efficiently, which results into faster switching. From a resistance perspective, due to higher mobility, NMOS transistors have lower on resistance compared to PMOS. Lower resistance allows NMOS transistors to discharge capacitive loads faster, thus leading to higher switching speed. Let's discuss about noise margin. NMOS transistors generally have a lower noise margin compared to PMOS transistors. This is due to the differences in the threshold voltage and carrier mobilities between the two. The threshold voltage of NMOS is lower than that of the PMOS, meaning that it can turn on more easily with small noise-induced variations in voltage. This makes NMOS circuits more susceptible to noise. In CMOS logic, NMOS transistors are used in pull-down networks, while PMOS transistors are used in pull-up networks. Since NMOS transistors switch faster and have lower resistance, the pull-down is stronger, leading to an asymmetry in noise margins. A stronger pull-down network leads to a much faster 1 to 0 transitions, thus reducing the low noise margin, which is VIL minus VOL. Here we have the voltage transfer curve of an inverter. As the pull-down network is stronger, the curve goes to low much faster with a stronger NMOS, which makes VIL and VOL much closer to each other, reducing the low noise margin. In CMOS circuits, NMOS and PMOS transistors play complementary role in determining the rise and fall times of signals. PMOS transistors are used in pull-up networks, while NMOS transistors are used in pull-down networks. Due to higher mobility of electrons compared to holes in silicon, NMOS transistors conduct current more efficiently compared to PMOS, thus reducing the delay. Since NMOS is faster, the fall time or the transition from 1 to 0 is typically less than the rise time in standard CMOS logic circuits. Here is the output of a CMOS inverter with equally sized NMOS and PMOS transistors. Due to the stronger pull-down action of NMOS, we observe that the fall time is significantly shorter than the rise time. Just as a recap, rise time is the time it takes for the signal to transition from 10% of VDD to 90% of VDD, and fall time is the time it takes for a signal to drop from 90% of VDD to 10% of VDD. Now let's find out how to get a balanced rise and fall time in design. We know that the PMOS used for pull-up network is weaker than the equivalent sized NMOS used in pull-down network. In order to get a balanced rise and fall time, PMOS must be stronger. Suppose a CMOS process technology where the mobility of electrons mu1 is 2 times of mobility of holes mu p. For this case, we make PMOS 2 times larger in size compared to NMOS to compensate for slower switching and get balanced rise and fall times at the output. However, this increases area and capacitance for PMOS and overall design. From a power efficiency perspective, NMOS transistors are more power efficient compared to PMOS. The on resistance for NMOS transistor is smaller and thus it has lower power dissipation compared to PMOS when both are on. NMOS transistor has a much smaller threshold voltage and requires a smaller gate voltage to turn on, reducing power consumption and reduced heat generation in circuits. Dynamic power dissipation in circuits is given as F times C VDD square, where C is capacitance, V is voltage, and F is switching frequency. For a balanced circuits, PMOS transistors are designed much larger than NMOS, which increases parasitic capacitance, leading to higher dynamic power dissipation in PMOS during switching. This concludes this video on differences between NMOS and PMOS characteristics. I hope this is helpful. Please post your feedback and comments.